Okay, so this video is going to serve as sort of a reintroduction to covalent bonding, and we'll start to look at Lewis structures. So we've already gone over metallic bonding, the electrostatic attraction between positive ions and delocalized electrons. We've gone over the ionic bonding, the electrostatic attraction between positive and negative ions. And we've talked briefly about covalent bonding, that it involves the sharing of electron pairs, and the attraction is the attraction between the positive nuclei and the shared electron pair, or multiple pairs as the case may be. So unlike metallic and ionic bonds, which could be called non-directional because they the attractions exist all around each particle, in covalent bonding the attraction is highly directional, and two very specific atoms have an attraction for one another, and that's where the covalent bond is and nowhere else. The types of structures associated with the covalent bonds usually are molecules, so small particles made of a couple of atoms or a small number of atoms that are bonded together and create a new distinct unit that we call a molecule. Of course, molecules can be quite large and complicated as we get to proteins and DNA. Those are technically molecules, but they are quite large. And then we also are going to have a couple of macromolecular structures such as diamond and graphite and silicon dioxide, which can't really be described as just simple molecules because they are so large. And nonmetals are the types of properties associated, are the types of elements associated with covalent bonding. And normally, molecular compounds tend to have fairly low boiling points and melting points relative to these other types of bondings, but the macromolecular covalent structures tend to have very high melting points and boiling points. And we'll get into that more in some subsequent topics. So normally when we do covalent bonding and Lewis dot structures, we're going to focus in on a rule that's referred to as the octet rule. And the idea is that usually atoms are going to covalently bond in such a way that the number of bonded electrons, so the number of electrons that they're sharing, and the non-bonding electrons, the ones that they're not sharing, give the atom a full octet, a full 8 outer electrons. So normally 8 electrons is a full valence shell, hence the name, the octet rule. There are, of course, some exceptions to this. Something like hydrogen, which is so small, only ever forms one covalent bond because for it to have a full valence shell only requires 2 electrons. So it's not really like it's breaking the octet rule. It doesn't need to go for a full octet. It just needs 2 electrons to have a full shell. There are going to be some strange examples that we'll get to in the video, which are called exceptions to the octet rule. And they will bond in such a way where they don't have full octet, and they are strange. They're exceptions, and they sort of just need to be memorized. So when we're drawing Lewis structures, we're modeling covalent bonding with chemical symbols. We can represent valence electrons as dots. We can also represent them as little X's or crosses, but I usually stick with dots because it's sort of the simplest one and the least messy. Inner shell electrons and the nucleus of any atom are represented by the chemical symbol. So putting that C there, this C is standing in for the nucleus of carbon as well as its inner shell electrons, and then we would put dots around it to represent its valence electrons. So carbon could be represented like this, a C with 4 dots around it for 4 valence electrons. Covalent bonds are going to be represented as line segments, but they can also be represented as dots between 2 atoms. So like if you wanted to show the bond between 2 carbon atoms, you could draw carbon bonded to carbon. You could also draw carbon dot carbon, and it would show that these 2 electrons are being shared. You can also show 2 carbon atoms, and you could do a dot and an X, which would imply that one of these came from one carbon atom and one of them came from the other carbon atom. That's fine, but it does start to get a little bit messy with all the dots and crosses. You should be aware of this, that it's allowed, because sometimes they'll show it on the IB exam, but usually lines are a lot quicker and cleaner. The non-bonding pairs of electrons, or the lone pairs of electrons, are going to be represented either as pairs of dots, pairs of X's, or as lines. So if an atom like oxygen has formed 2 covalent bonds but also has 2 lone pairs of electrons around it, you could draw it like that, or you could draw it simply with all lines like this, and it would mean the same thing. So a line segment represents 2 electrons. It represents an electron pair, the same way 2 dots does. And so whenever you draw a Lewis structure, it's essential that you draw all the covalent bonds and all of the non-bonding electron pairs to get full marks. So simple Lewis structures, everything obeys the octet rule. They should be fairly easy to figure out based on the number of electrons that things start off with. So hydrogen has 1 electron and chlorine has 7. And so in order to feel like it has a full valence shell, hydrogen needs to make 1 bond. That will make it share in total 2 electrons, and chlorine needs to make 1 bond in order to feel like it has that 8th electron. And so what we should recognize right off the bat is that's pretty simple. And they're each just they're gonna form 1 bond with one another, kind of an exaggerated bond there. And that gives them each a full octet. So now by sharing 1 electron with each other, so hydrogen had 1 to begin with, chlorine had this 7 over here. Now these 2 electrons are sort of felt by both atoms. And so hydrogen feels like it is these 2, and chlorine feels like it is this 8. And so they both feel like they have full valence shells. So as you practice the simple ones, it should be fairly straightforward. You should learn very early on that H only ever makes 1 bond. And figuring out how many bonds something makes should be easy because it's really however many electrons away from the octet it is, that's how many bonds it's going to make. So chlorine is 1 away from having an octet, so it makes 1 bond. Oxygen has 6 valence electrons from being in group 16, so you know that oxygen is normally going to make 2 bonds. Since hydrogen only makes 1 bond, it's pretty simple to draw 1 bond to one hydrogen, 1 bond to another. And in order to get the full outer shell, you give oxygen its lone pairs. So oxygen feels like it has these 8 electrons here, hydrogen these 2, and hydrogen these 2. So oxygen has 2 bonding pairs of electrons, and it has 2 non-bonding or lone pairs of electrons. Okay? So these are the simple examples, and we'll do some more practice in class. A quick introduction to organic molecules. Organic chemistry is the chemistry of carbon. And although that seems very specific, there's actually more compounds based on carbon than all the other elements combined. It's this amazing element that forms 4 bonds and creates long chains and rings with itself, which is why organic chemistry is so complex. So the nice thing about organic chemistry, though, is that all the elements are always going to follow the octet rule. So carbon's always going to form 4 bonds, and normally it will form these chains with other carbon atoms. Hydrogen only forms 1 bond, oxygen 2, and nitrogen 3. And so even though the formulas can get quite complicated looking, once you practice a bit, they actually become even simpler than the other examples that we try to draw, because you pretty much know that you should connect the carbon atoms into a chain and put the hydrogens all around the outside, and then figure out the remaining issues. So for example, here when I see C2H6, I know that hydrogen can only make 1 bond, therefore it's going to go on the outside, and I therefore know that the carbons are going to be connected. So I would draw the 2 carbon atoms and start off by connecting them with 1 bond. And then if there's 6 hydrogens, probably logically going to be 3 for each carbon. So 1, 2, 3, 1, 2, 3. And now I can see that each carbon has the 4 bonds that it normally makes. Every hydrogen is going to have the 1 bond, and so I'm done. So the organic ones, although they start off looking complicated, are actually going to be some of the simplest structures that we have to draw. If we try maybe one more example of a longer one, you'll see that this is sort of an odd-looking molecular formula. It's sort of broken up, and it's showing you a bit more about the structure, because as molecules get larger in organic chemistry, there become more options on how we can put them together. But if I try to follow this one, it says CH3, so C, and then I would put 3 bonds to it for H's. And then I see a CH2 comes after that. So I know the carbons are going to be attached. So there's the C of the CH2. So here's the H2, one hydrogen off each side. That's connected to a CH2, so there's CH2, and that's connected to a CH3. And for the sake of time, I won't draw in the hydrogens, but they would be required. But that's how I follow through one of these condensed structural formulas, as they're called. Just knowing that the carbons are going to normally be attached, unless there's something funny going on in the formula. And so I fill in the H's always on the outside, and very quickly I can draw the structure, everything obeying the octet rule. Okay, we've talked about this briefly when we introed the types of intramolecular bonding, but the bond length is the distance between two nuclei when they're bonding. And the bond strength is a term that is usually like a relative term when you're comparing the attractions of two covalent bonds. A more quantitative measure of bond strength is called bond enthalpy. And it's the energy required to break 1 mole of a bond in the gas phase. So a way to represent that would be like taking a mole of H2 molecules, splitting it into H atoms, or taking a mole of methane and splitting a whole mole of hydrogen atoms off of it. And the energy required to do those things is what we call the bond enthalpy. So as bonds become stronger, it takes more energy to break them, and therefore you'll have higher bond enthalpy values. So bond enthalpy values are always listed as positive values, endothermic values, because it takes energy to break apart bonds. Bonds are attractions. They are positives and negatives being held together, so it always takes an energy input to break them apart. And the reverse will therefore be true for bond formation. So anytime you break bonds, you have to put in enthalpy, or you have to put in energy. So you start off with the bonded atoms, and afterwards the unbonded atoms have more potential energy. They are less stable. And when bonds form, that is always exothermic, and energy is released as the atoms come together and attract one another. So we've talked about this briefly, and we'll leave this for class to look at these data table booklets on covalent bond lengths and covalent bond strengths, and with bond enthalpies. They're listed right side by side. We should be able to come up with some factors about atoms, about the number of bonds, and see some very distinct trends for what things affect bond length and bond enthalpies. And here's some practice questions for class. We'll end this video with some exceptions to the octet rule. For the SL class, the only exceptions to know about are beryllium and boron. They're very unique elements. They belong to groups 2 and 13 respectively, and those groups are normally groups that contain metals. Metals have very low electronegativity values, and so usually don't form covalent bonds. Usually metals engage in either metallic bonding or ionic bonding when they're with other nonmetals, or with nonmetals. But because beryllium and boron are super small, they're in group 2 or row 2 of the periodic table, they have very little shielding effect, which means they have very high electronegativity values for their groups, for their families of elements. And so they, unlike the other elements in their columns, tend to form covalent bonds because of those sort of high electronegativity values. So that's why they end up being the exception. There aren't many things that have only 2 valence electrons or 3 valence electrons that actually do covalently bond, and that's why these are the ones that show sort of strange structures. So beryllium only has 2 valence electrons. If we were just going to draw its dot structure, it looks like this. So it only has 2 electrons. It only has 2 electrons to share. So beryllium bonds and forms a compound with hydrogen where it forms 1 bond with each hydrogen. Whoa, that was a big H. Sorry about that. And that's it. This is the molecule. The beryllium does not have an octet. It only experiences, like it has 4 valence electrons, but this is how it forms. And it's because of the fact that beryllium only has 2 valence electrons to share, so it forms covalent bonds with, or compounds with just 2 covalent bonds. Boron, similar idea. Boron starts off with 3 valence electrons, and so boron forms compounds with just 3 covalent bonds, making it feel like it has 6 valence electrons. And so there are the 3 bonds. And so while these are odd and they may frustrate you because you want everything to obey the octet rule, for every rule there are exceptions. And these are the two elements to be aware of. They form compounds with less than an octet of electrons. They can form what are called polyatomic ions, which have charges that then have the full octet of electrons. But for now, when they are uncharged, there's no way for them to actually get that full octet. And so this is what they look like.